Hey, how's it everyone? I thought I'd quickly give you an overview of a cool piece of tech called WebRTC that I've been playing with for a couple of days, and I think it's pretty exciting. So the idea of WebRTC is that it sort of allows a web app, a browser-based web app, to connect in a peer-to-peer way to another browser web app fundamentally. So it's almost like the idea of trying to take two browsers and connecting them directly to each other. So, and potentially, like over the internet, right? And so why would you do this? Probably for a bunch of different reasons, but one pretty good one is for media. So moving video and audio between two browsers. So if you were going to have a video call with someone, ideally the best way to do that would be to connect the browsers directly together, so that you can have the lowest latency potentially between those two browsers. So it's kind of a bit different because the web typically is like a client and server type of architecture, whereas something like WebRTC is saying there's almost no need for a server. Why not just connect the browsers directly to each other? Now obviously it doesn't work exactly like that, and your browsers can't connect directly to each other. They have to probably use some kind of service in the middle which coordinates them connecting to each other. And in WebRTC world, that's often called signaling. So I'm going to use a mirror board over here to try and draw what that may look like. So effectively we've got like kind of a browser and another browser, and maybe these browsers want to connect directly to each other, right? Now they obviously kind of can't, like your browser doesn't really listen on a port on the internet, so how would they do that? So typically what would happen is, in a WebRTC world, is you would have some kind of server in the middle called a signaling server in this browser, and the signaling server is really up to you to build. So it could be a RESTful thing, or it could be a WebSocket or whatever it is, but that browser probably talks to this thing talks to this thing, and they somehow, the signaling server would exchange a piece of information between each of them in order for them to talk to each other, or to be able to connect to each other directly, if that kind of makes sense, right? So one of the challenges with this kind of model, and obviously we have like the internet between these things, is that, from a typical internet infrastructure perspective, you wouldn't ever really be able to have a client connect directly to some other client, especially if they were browsers, right? So you've got kind of problem, like you've kind of got like the NAT type of problem. So what is the NAT problem? It's really that this browser is sitting probably within the scope of an organization. It could even be your home network, it doesn't really matter. And that home network has probably got some kind of router or something. So here's our browser, this is our network, and we have some kind of router, and that router, sure, connects us to the internet, right? And so he has a public IP address, which means that he is addressable by other clients that are directly connected to the internet, so that they can find that router on the internet. However, how does this browser then expose itself onto the internet, right? Assuming that browser is connected to that router, and you may have other things on your network as well, maybe your phone, your iPhone. And so this is really like and this is called a NAT problem. So network address translation means that this browser, although it gets out onto the internet and connects to the server potentially here, when it does so, its source address is changed to reflect the router's source address, so that when that request gets to the server, it gets processed, and the server then replies back by flipping the source and the destination. It then hits this router, and this router has to be smart enough to go, oh, wait a minute, that request was initiated by this client, and so I should probably deliver the reply back to that client. And what he's doing is he's doing network address translation. So he's translating from the internal address of this browser to the public address out here. So that's what NAT is. So if we think about our original diagram here, where we had two browsers connecting to each other, it's actually a lot more complicated, because in fact each browser is really, if you just to kind of make it a bit more detailed, we've got these two browsers, here they are. Effectively there is some kind of router probably sitting here, and we've got the big internet here, we've got another router here, and that goes like that. These guys can probably see each other over the internet, but they somehow have to figure out who, when one is connecting to the other. Typically you can't initiate a connection through a NAT kind of network. What typically happens is that the client initiates the conversation to the server, and then the server responds. So NAT works well when it's based on replies. So replies coming back into the internal network, NAT can deal with. But where the server initiated a connection down, there's no way of this router knowing who to direct it to, because it wasn't initiated internally, if that makes sense. So that's your NAT problem. So what happens with WebRTC is we have that fundamental problem, that neither of them, they're both initiating, and they need to connect to each other. So we use the signaling server, as we said, which exchanges a piece of information between these two things in order to help them find each other through their routers. And that little packet of information is called, or that protocol for exchanging how to connect to each other is called SDP. So SDP actually is quite an old protocol. Actually got it up here. So SDP stands for, what does it stand for? I googled it. Session Description Protocol. So it's a way, I think it was invented back in the days of VoIP, so making voice over IP calls between clients. They created a protocol called SDP. I'm hoping maybe we could find an example of what it looks like. It's quite a nasty looking protocol. Yeah, it kind of looks like this. Oh, that's a video. But, it'd be cool if we just show us an example. Annotated example. Yeah. Really basic example. Yeah, it looks a bit like this. It's kind of like a key equals value type of text type of protocol, and so within it is a whole lot of media type info, so port numbers, etc. But you may even see things like multiplexing. Okay, no, so it's mostly it's IP address stuff, but it also includes some media type stuff, so audio, potentially, maybe bit rates, the types of encodings, etc. are in this SDP protocol. So it's quite a nasty format, but it doesn't really matter as long as the this client browser 2 can generate one and pass it to the signaling, and browser 1 can generate and pass it. Signaling can exchange those two SDP packets to each other. It sort of contains the solution as to how to connect to each other. how these two browsers can connect to each other, even through a netted infrastructure, even if that netting is on both sides. So when building this SDP packet on the client, well, on that browser side, he has to build up this SDP. He needs to put in enough information into this packet to give the other side a chance of connecting through to him. So SDP uses something within the packet called ICE, ICE, Internet. I can't remember what it stands for. Another TLA, ICE protocol maybe. So ICE stands for, maybe it was in here, Internet Connectivity Establishment. So effectively what ICE is kind of a list of different ways that this browser could be connected to, and he'll put a bunch of different options into the ICE packet, so they call them candidates, ICE candidates. The first one could be just a simple, he may just say, you know what, I'm going to use, so I'm not sure if anyone has heard of something called UPnP, Universal Plug and Play, but this was a protocol invented a long time ago where a client certainly on a home network, if this was a home network, that router may support something called Universal Plug and Play, where a browser or any client could message that router and say, hey, I'm about to receive an incoming connection from the internet. Don't you just want to pass it to me when it arrives? And what that router would do is he would kind of assign that client a unique port number that he would open up on the internet side, and any connection coming into that port, the router would then sort of ahead of time know, oh yes, this is for this particular client, so let me route it directly to it. So that's UPnP, and this is something that you may have on your network. My router doesn't have UPnP, so it's an option, but it's certainly one of the candidates. So what the browser could do when he's building the SDP packet, and remembering that ICE is just a piece of the SDP protocol packet. There's other stuff in here like the media and the streams and the bitrate and all the things that he supports, but ICE dealing with the connectivity piece. So UPnP could be one. So what he might do is he might ask the router, hey, like, configure yourself, give me a particular port number, give me your internet IP, and he may just put that as a candidate in the packet if your network does support ICE. So he might put a public address and some kind of port in there. But that might not be compatible on your network. You may not have support for UPnP. So your browser then needs to build up a couple of other candidates, which are the options. So another way that they could connect to each other is through something called stun. And there is another one called turn. So you've got these other options called stun and turn. And these would only come into effect if you were on a natted network. If you weren't on if your client, your browser wasn't natted at all and was directly connected to the internet, it could just put its public IP and port and be done. That's the only candidate it would need. So what does stun and turn stand for? Because I don't remember. Stun versus turn. Stun server. Session traversal of user datagram protocol. And it says through network address translated server allows NAT clients to set up phone calls to avoid provider hosted outside of the local network. Yeah. So what stun will do is allow, so a router that doesn't support UPnP, Universal Plug and Play, effectively what it is let me draw another diagram. We've got our browser again, and a router. Sure, and this is on your home network, and this is really a dumb router, so he's really just going to route packets out. Obviously he supports NAT though, so he has to translate from the private side to the public side over here, and that's really the NAT. So what this client could do without having any support from the router is he could connect to a stun server living on the internet. This browser could connect directly to it and just say to the stun server, hey, what is my source address? Where did this packet come from? The one that it's just hit you. And obviously what he would end up seeing is he's going to see the address of the sender, which is really this guy here. So what the stun server would do is he would just reply back to the client, and effectively what they would allow the browser to do, or the client here, is to know what his public source address was. So they were effectively the address of the router. So that would, by a stun, allow him to also derive effectively a public address with a port number, because obviously there was a source address as well as a source port that appeared here. So that's what stun effectively does. So you could have stun type addresses in here as well. And that may be good enough, because it might be that when a client out here connects to that same source and port over here, that router might be dumb enough to say, no problem, I'll just pass that through to this client. But you've got to be a pretty dumb router for that to work. A smart router is going to say, hey, wait a minute, this particular source and port was destined for this service here. So if another client connects in on that same source and port here, this router may choose to say, no, wait a minute, this seems to be coming from another address. So stun doesn't often work. And so then we have something called turn. So what is turn all about? Turn is, who knows what it stands for? Turn server, let's have a quick look. It's traversal using relay net. So what turn does effectively is, let's just kill, I'll just use the same diagram. Effectively what a turn server does is this client connects through his router to the turn server now, and he says, hey, how's it? Don't you want to allocate me a public IP and port? And when you get connected to, effectively pass that traffic back to me. So this connection stays connected long term, and however that address there gets passed back to that browser. And so when that browser then advertises his address in that SDP packet, he would advertise the turn server's public IP and new port number. So any new client, so a client that now thinks that he's connecting to this browser here, may connect to that port there, and what the turn server will do is it will just tunnel that traffic back down that same connection back to this browser. So effectively, and that would be for all traffic, so it would mean that the media, whatever's passed from this client back and forward, would traverse through the turn server. Whereas if we just used a stun server and we just identified our source and port, this client would be connecting directly to that source and port, right? Meaning that there's no traversal of traffic through any relay. So effectively a turn server is kind of what I would call like a relay. Is the traffic will be relayed through it. Not really processed by the turn server, so that turn server can be pretty dumb. Doesn't need to do anything with the traffic. It's simply just relaying in order to defeat the net problem, if that makes sense. And of course, yeah, so from an ICE perspective, your client may decide to put a number of different candidates into the internet, because your browser, fundamentally doesn't understand your network topology, so it puts a bunch of candidates into this SDP packet to give any other client that's trying to connect to it the best chance of getting through. And ideally it works through either like a UPnP or a stun, because these two mean that the clients connect directly to each other. But at worst case, you may even have a turn server or a relay. So if these two fail, the traffic could still get to them via relay. But of course, you're going to have the highest latency at this perspective, as well as potentially, this is not really peer-to-peer anymore. Your browsers are connecting directly to each other. So it's kind of like a fallback, but kind of in a secure network, or even in a secure home network, you're going to find that turn is really the only option. Okay, so just to summarize then, now that we've been through all of that stuff, when you are building a WebRTC type of thing, or a solution that uses WebRTC, so the ability to pass media between clients. Your architecture needs to incorporate a bunch of different components. So of course you've got your app, which could be a web app, and you are going to need a signaling server. So signaling, just to reiterate here, signaling server isn't anything very specific. This is totally your backend. So whatever your service is, if you're writing a RESTful service or a SOAP service or whatever it is, you just need to incorporate a bit of signaling into your app. And effectively what that is, it's just a way of being able to, so say for example your app wants to support the ability for the client to dial another client, or maybe you're creating the concept of like a video call center. Somehow this app needs to tell the signaling server, hey, I'd like to phone the call center, right? And that app needs to pass an SDP packet to that signaling server. And that could be through just one of your standard RESTful calls where the SDP packet is just one of the fields within that JSON request or whatever. And then when that signaling server determines, maybe he then chooses from a list of call center agents that it wants to connect them to, that signaling server would be responsible for fetching an SDP from that agent. So maybe you've got kind of agent 1, and you've got agent 2, and this is up to your app, right? Maybe your app, your customer is trying to dial into a call center, and you've got 2 available agents. The signaling server then, or your server, needs to determine, oh, okay, I'm going to route this to agent number 1. So it somehow needs to determine and fetch an SDP packet from that agent, which is then exchanged with that application, and the SDP that came in from the app is exchanged with the agent's application, and then so that they can initiate a connection between each other. And then we talked briefly about how that's quite hard because you've got the internet here and you may have netting happening on both sides. And so then you really do, if you're building a WebRTC interface, you have to take care of 2 other things, one being a stun service and the other being a turn service. And these have to be hosted somewhere on the internet so that these guys can, when they're forming that SDP packet, can go and get the help of these stun and turn servers in order to do that. So that when they connect, either they do connect directly to each other and they've discovered their addresses through stun, or they connect to each other via relaying those packets through a turn server to each other. So when you're building a WebRTC app, you really have to think about not just your app and not just your backend. Your backend needs to support a new bunch of functions around really the signaling and the exchanging of these SDP packets, as well as you do need to somehow support the ability to have a hosted stun server or to deploy your own stun and turn servers on the internet. So I had a quick look on AWS, and actually I hadn't discovered this until now, but Amazon Kinesis video streams does support fully hosted turn streaming minutes. So you can even use AWS. So if you are building a WebRTC type of app, it looks like they also support the signaling piece, so they can have a fully managed signaling piece. That piece I think is probably the least important, because I think the logic of signaling is probably your application backend's concern. But maybe AWS supports a bunch of standard type of coordinations here. So that's pretty cool. But most importantly, I think, is the ability to have a fully hosted turn service provided by AWS. And you're looking at, so it's the number of minutes per 1,000, I don't know, 13 US cents per 1,000 minutes of turn streaming. So that may be worth doing, because certainly in my in my experience, I launched my stun and turn service on AWS on an EC2 machine. So I just launched an EC2 server, EC2 machine, ran a piece of open source software called CoTurn, which supports both stun and turn together as a single unit. But that was a bit of a pain, and I really don't like supporting running individual machines, and of course you'd need to make it highly available somehow, whereas AWS's fully managed turn streaming service could actually just be perfect, and I don't think that's a terrible price either. So that's certainly one option to deploy these. Okay, cool. So next, let's actually quickly build a very small example of a WebRTC client, and let's see if we can get it going. Let's make a quick directory, and then I'm going to use view. It really doesn't matter. I mean, most of the WebRTC, actually all of the WebRTC is just implemented as pure JavaScript, so you can use whatever JavaScript thingy you like. I prefer npm. And quickly build a very tiny view app. Wait for that to finish. Okay, cool. So let's just launch it. So I'm going to make it bigger. Run serve. And let's see what our view app looks like. Click that. So it's opened in a different tab. Put it there. Okay, welcome to your view app. Let's open the source code. That folder. Okay, so the first thing with any view app is you kind of got to get rid of all the usual junk that's in here. But probably what we want to do is create a new component. So let's just call this like a, I don't know, the video component, right? And with any view thing, we've got a template, we have a script, and we have a style, a style, yep. And then I never remember exactly what goes into a component, so let's just props. Okay, so that looks like good stuff. Export, oops. Export default, okay, yeah. We don't really need props, but we do need a component name. Okay, cool. So the template, let's just start with something dumb. Make sure it works. Video goes here. Then let's see in our app, I think we have to import the component here as a video. In fact, we can just destroy this silly one. Video, and import it from that component. We don't want any of this stuff. And we just want a video there. I don't even think we want their style. Let's trash all that, and we should see video goes here. Cool. Sorry, I just lost my recording now. So you may have missed a few things, but effectively what I've done is I've added that local video element at the top. Effectively, I've got a button that when you click it, it calls the get media function, which is down there. That get media function effectively sets the stream object, which is now a data on my component, and it calls navigator.mediadevices.getUserMedia with a constraint of video equals true. I think I could also go audio true, so I want video and audio when I call getUserMedia. I wonder if I should maybe make this the bottom of my screen. It might be easier to see. Yeah, so if I now hit my app and I click Get Media, yeah, so you can see I've probably already accepted the permissions, but you would have popped up a thing saying, hey, this app is trying to access your webcam. Are you okay with that? And if you said okay, you see this little video thingy appearing here. So I can see that camera and microphone are allowed. This page is accessing your camera and microphone, and so that's cool. We're obviously capturing audio and video now, but we're not displaying it anywhere to the page. And so that's what this stream thingy has probably got that audio content in it. Okay, so let's have a quick look at that tracks object. I just want to move that up there and have a look at it. I'm not sure if this is going to be useful, but let's log this.stream, see what that does, and let's open up the developer tools. There it is. I have to refresh it and do it again. Get media. There we go, cool. So our stream that we got back from Get User Media is a media stream. It's active, whatever, all that kind of stuff. And then we can do more with it. So the stream contains a number of tracks. I'm not really sure what these tracks are, but this is what you kind of got to do. You got to go stream.getTracks, and this will give you back a list of tracks. So var tracks equals that. Let's console.log those things. So tracks could obviously be things like a video track and an audio track, that kind of thing. Stream, this.stream. Click it again, get media. Yeah, so we got two tracks back. Both of them are media stream tracks. One is a video, one is an audio. They've got different IDs, and then quite interestingly, they're both labeled. So the one is like my default USB audio device. The other one is a USB camera. So and then using other functions, there is the ability to find to use different webcams, different audio devices, etc. using this get tracks kind of method. I'm not going to dive into that. Let's rather just see if we can throw that video track up into that element, so we could at least see it working. It's going to be interesting because I am busy recording through that same webcam using another app, so it may or may not work, but let's try. I think all we actually have to do is we can take that entire stream and throw it at the element, as it seems to be. So I can take the video object, so I just need to get a handle to this object, right? Let's just do it in the kind of dumb way, which would be document.query selector, and this is an ID of local video. Yep, this would give us our video element or something, and then we want to go video element dot source object equals that stream. So this is just kind of hacking it in the back. Equals this dot stream. This is really, I'm not using Vue very well here. I'm literally using JavaScript element directly, and I'm just hacking source object straight into that video element's DOM. So it says get media. We get that with a cool background echo because the audio is going through as well. So we probably want to trash the audio. Let's not pass audio for now. We get media. Cool. We just get the video coming through. That's brilliant, right? Okay, cool. So we've got the ability to get the local user media. I think the next thing we should probably look at is we need to build the beginnings of our signaling server or our backend, because the next thing we're going to do on the web client really is to try and initiate a peer-to-peer connection, and we can do that, but we do need to pass that through to our backend, and so I'm just gonna start with that. So I'm going to build a signaling app quickly. Let's just go there. I'll maybe make a new tab. Oh, sorry, it's that. Oh no, I don't want to update that. So let's go to the signaling, and I'm going to just I'm just going to build a very quick WebSocket project here. So I've done npm init, sorry. I'm going to go npm install. I think the one I'm looking for is Node.js WebSocket. Yeah, WebSockets WS. So I'm pretty sure I just do an npm install of WS. Cool. So I'm going to save WS. Let's go new file here. I'm just going to call this main.js, something like that. And cool. Okay, so what does a WebSocket app look like? We're going to go var, so we're going to import it. WebSocket equals require WS, and then a WebSocket service. I think actually, we can probably see an example over there. Okay, so require that. So it's a constant, seems fine. WebSocket.server. Probably don't need all of these options, but I could give it a port number. 8080 sounds fine. That's probably good enough. Sorry, port 8080. And then so on, it's got this kind of listening interface. We get a function which takes nothing. I suppose I could use ES6 type stuff. Let's do that. We can go console.log. Started listening. That's great. WSS.on. So this is the important one. It's on a connection. So when a client connects, we get given a connection. It's actually really the WebSocket. You should really call it the WebSocket. But that connection, so I suppose we could log here, new connection. But on that connection, we can then on again message. Yeah, so this would then receive a message per connection. Is a console.log received. Let's use this. Received message from client or something. And then I think it can disconnect as well. Yeah. So connection dot on close. So get to a little console.log client disconnected. Okay, so we can give that a little test. Let's go node. What do I call my app? Main. Oh, sorry, this does need to be equals new. Okay, start listening, and then I've got a cool little test WebSocket client. I don't know what it's called. Simple WebSocket client is an extension to Chrome, so I can test that out. Localhost on port 8080. Let's try it. If we go open. Doesn't work. Close. Started listening, port 8080. I wonder if we need like a URL here. Okay, so it looks like I just had the wrong port. Something was probably already listening on port 8080, so I just changed it to port 8001. Port 8001, relaunched it there. And if I go open, it says opened, and I can send a message, hello. Send, and I received hello from client. If I click close, I get client disconnected. So that's cool. So I've got a signaling server, the beginnings of what could be a signaling server in the middle. Effectively, what I'm really looking to do in this example is probably just build an echo, like a broadcast echo server. So any connection in from the web app will connect to the WebSocket server, and really he's just going to pass messages through that WebSocket server out to all the other clients for now, just as an example. Okay, so let's build that echoing, that broadcasting sort of functionality. It's actually pretty simple. So every time I receive a message from a client, what I want to do is for all of the WebSocket servers clients, effectively run a for each, and I'm going to say for each client, and I want to just really write it to that client. So as long as that client is not me. So if client is not equal to the connection, and the client, I don't know whether I need to do this. Let's just do that. We're going to go client.send that message. So we could even put a little log, console.log, broadcasting message to client. Something like that. So if we now test this thing, we send hello, we're not seeing it sent to any other client because I am, this client is the only connection. So it's not sending it to itself. But I wonder if I can open another simple WebSocket client. So I can open that. If I click that, do I get a new one? Yes, I do. So that's cool. So let's open up another WebSocket client. Go open, another one will open. I go hello from other one, and I click send. I get hello from other one there. Although I also got it here, so that doesn't look great. Send it here. So it does seem to be broadcasting back to itself. I think that just seems, that's literally an issue with the WebSocket, with this extension. It doesn't seem to actually be broadcasting it. So if I look at my back end, I'm only seeing one broadcast message to client being written, and if I disconnect one and I send from there, I get no broadcast messages. But if I open it twice, I do get a new connection, and if I send, I get one broadcast. It does seem to write it back to both simple WebSocket clients though, and I think that's the extension that's doing that. It's not my server. So I think the broadcasting functionality is working. That's probably good enough for us for now. Okay, so let's go back to our main View app, and let's have it connect to our WebSocket. So what I might do is, I think just I'm going to kind of build it out through these buttons so we can see how stuff goes. So the first one might be connect WS or something like that. Connect WebSocket. So let's write a function to connect the WebSocket. And it's going to be an async function. So let's do that. We may want to keep a handle to it, I guess so. So let's go WebSocket is null to start. Connect WS is going to go this dot WebSocket equals new WebSocket, and I think a WebSocket literally just takes the address. So we have the address up here. Sorry, here it is. So we can connect it like that. And then we can do a bunch of .on type of stuff. So this dot WebSocket dot on message equals a function which takes an event, and this is console.log that event. Actually, I might go like this, on message, or go like WebSocket.onMessage or something like that. Okay, cool. So let's see what that does. We go connect WebSocket. Yes, so we got a new message. Let's just do that again. Connect WebSocket. We have a new connection appearing on our server, and we can't broadcast anything to it yet, but we've got our DevTools here. But if we write from the simple socket hello, and we send that through there, yes, cool. So we had the on message run. The message event is on trust, or the data of hello, fine, cool. So we've got WebSocket with kind of broadcasting sort of working there, which is great. Okay, so let's start with, so we can connect our WebSocket, that's cool. We may come back here and add some more things as we handle those messages. But let me just change the order of these buttons. The next thing we're going to do is we're going to begin to set up the RTC, the WebRTC connection. So I'm going to make a method called start RTC maybe, and we'll call this like setup RTC connection, or something like that, right? So we're going to set up RTC connection, cool. What did I call it? Set up RTC. Let's make that function here. And effectively we're going to use a thing like this. If we Google it, WebRTC peer connection is the object we're going to use. So this RTC peer connection it's kind of like the socket that represents the connection between me, my browser, and my remote browser. So that is one peer connection. If you're going to build an app which has connects to more than one browser, each connection, you would have to have more than one connection. So one connection is a peer connection. It's between you and another client. If you're going to connect to 5 clients, you're going to have 5 peer connections, one representing each connection. So this is what we're going to create. We're probably going to keep a handle to it. So I'll just call it the peer connection in our structure, and we're going to say this peer connection equals new RTC peer connection. And I think from a constructor perspective, the important thing here, there's obviously a bunch of different properties that you can put in, but kind of the primary one is our ICE servers. So remember, those ICE servers are the way of, it's that property within the SDP packet that will be generated, which contains how all of the different potential ways that you could connect at the underlying, how many different protocols there could be. So what I'm going to do is, just for this tech session, is I'm not going to launch my own turn server, but there is actually a public available stun server. So on Google does host stun, and stun, remember, is very light. It's just passing of addresses to clients. They don't host a turn server because that would use a lot of bandwidth, but I'm going to just provide a basic stun server for now. So I'm going to create so you can obviously provide a bunch of different servers here, but I'm going to just pass a simple Google stun server as my set of ICE servers on my peer connection. Then on peer connection, we've got to do a bunch of different work here. I'm just going to paste these. So the first thing is we have to handle on ICE candidates. So this means that our browser is going to start trickling ICE candidates together. So that means like the browser is going to start to figure out as it connects to a turn server or a stun server, it's going to get results, and it's going to pass those results in a streaming kind of way to this peer connection. So this is locally receiving local ICE candidates, and you can handle them somehow. The best way to handle them probably is to pass them to your signaling server, because your signaling server needs to know each of these candidates as they arrive. Another function we need to provide is on add stream. So this is our local stream. So when we add our own local video play, what are we going to do? And then we can also do on remote stream. So this is when a remote, the other side of the peer connection, passes us a stream. We can also handle that. Yeah. So when we get a remote stream, okay, I'm not quite sure how to handle that one yet, but certainly one of what we should do is on ICE candidate. Let's just first look at this. So we'll go console.log on ICE candidate, and then log the event. That could be a cool thing to do. The event is defined but never used. These guys. Let's actually just log them. This is on remote add stream. This is on the add stream. Okay, and let's just try it. So let's go set up RTC connection and see what we got. Did we see anything? Set up RTC. Did this not call? Start RTC. Oh, okay, yeah. So I mean, we've just created the thing. These things haven't started dialing. We can put our local stream. So remember our little local video element. We should attach that as, here was our video element. Oh, this dot stream, right? That's our local stream. We can pass that there. So we can say add stream there. So not type of, because we didn't call media yet. Let's just do that. Get media, set up RTC. Okay, so none of these functions are actually firing yet on remote or on add or on ISAT candidate. It's because we're missing the kind of calling. We haven't yet connected our socket, and that's probably the next thing we should do. So so that's kind of a setup. Let's go call. I'll just call it call. Make a call. Right. Okay, let's make a function. Okay, what is call going to do? Call is going to, on our peer connection, it's going to call a function called create offer. I'm just going to paste this in. Yeah, this looks good. So it goes this dot peer connection dot create offer. So there's kind of two parts to a peer connection. The one is the offer side, so the person initiating the connection, and then there's the answer side, so the person who's answering that connection. So you're either the initiator or you're the answerer. So the offerer and the answerer. Of course, when we click the make a call button, we're the initiator. So we're going to call create offer. Create offer takes two. It's kind of two callbacks. The one is a session, obviously the session description that gets created, and then the other one is obviously like the error handler. And that's cool. I think that looks good. Let's go console.log here. Create offer error. I see something like that. Oh, I've got some syntax error. What is it? An extra closey thing there. Did I not in my call? Oh, I've closed that there. Sorry. Should be a comma here. Okay. Okay, so call will call create offer. So let's go to get media, set up RTC, make call. Look at our debugger. Cool. So we got setting session description was called RTC session description. So we got an offer, and then here's the magical STP packet. So effectively, what it's happened is when we called create offer, the WebRTC peer connection generated us an STP packet. So if you want to look at that thing, you're welcome to, but probably inside it, we may find some interesting address information, etc. Maybe not. I don't know. You're welcome to look at it. However, the thing is that session description doesn't need to make its way down to our backend. The cool thing is it's already like a JSON object with type equals offer and then STP as an envelope. So I'm just going to pass that whole structure as a JSON structure to our backend like that. So it should just be this .WebSocket send message. Is it send message? No, it should just be that .send, right? With session. description. Importantly though, and I'm not sure where this thing comes from, but we do have to go, we have to set on our peer connection, this .peer connection dot set local description. I'm not 100% sure why we need to do this, but maybe it's to say that our local description is this SDP. I don't know. Okay, cool. So let's make that actually work. I don't know if this is going to print, but let's send it to our backend and see what happens. We connect the WebSocket, set up that, make a call, and that doesn't send because it can't read the peer connection of undefined. Oh, and this is probably because of this problem. Could it be? Let's just try that, the good old that solution. Let's try that, get media, connect, set up, make call, yeah. Okay, so this changes based on, so the callback to create offer, the callback, sorry, into this function session description, this switches around and it's no longer the view component. So I can't just go this.peer connection. So I've just solved it with a that. Probably not the best way to do it, but we have received some object. Okay, so session description from client. That's probably wrong. We should probably be encoding that thing. Yeah, so when we send this to our socket, let's stringify that object to agree. Get media connect, set up and make a call, and then there goes the big SDP with type equals offer. That's cool. And if there was any other client connected, so maybe our simple WebSocket client, there we go. The simple WebSocket client would have received, any other client would have received an object with type equals offer. So we should probably handle, so next I think we should probably handle that type equals offer thing if we're the other client. So on message, here we go, we can say, so I think it was event.data is actually our object, and we can go like const message equals java.json.pos event.data, and we can kind of do like a switch statement here. I'm just going to cheat and go if message.type equals offer. So this means we're the client who's receiving an offer. So how do we handle receiving an offer? All right, so we've got the create offer function working when we press the make a call button, well, we hope. And now we need to handle it on the other side of the peer. So this means we're on the receiving end now, we're receiving an offer. What do we do with it? And obviously what we need to do with it is we need to create the answer. So let's do that. So we know message.type equals offer, that's cool. So the first thing we've got to do is we've got to set a remote description on the peer connection. So it should be this dot peer connection dot set remote description. And although message contains it, it's like we have to give it this object, RTC session description based on that message. So that would set the remote description. We're still going to set the local description. So remembering that the guy who created the offer has set his local description. We should see it there. He set his local description. Now the dude receiving the offer is going to set the remote description. He also has to still set his local. And when the answer is received, the other guy will set his remote description. This is effectively the exchanging of those STPs, technically, yeah. Now we need to create an an answer, and that answer looks almost exactly the same as the create offer with the two callbacks. So I'm just going to cut and paste it. Something like that. Create answer takes a session description. Setting session description, let's say setting create answer session description, and let's make this one the setting create offer session description. Okay, and he's going to set his local description of that. That's awesome. And then he's going to send that back to the WebSocket. So that would now create an object of type answer. We can actually maybe see this working. Okay, let's see if we got some this problems. This, oh, that, this and that. Oh, okay. Yeah, this should be this, right? That is not defined on 91. Oh yes, because we thatted these thingies. We're probably going, yeah, this is the problem. We're probably going to have exactly that same issue. So let's just sort this out. We'll go that equals this. So we can keep a handle to our view. Our view component, because we're going to access peer connection and WebSockets, and that belongs to the component. Okay, cool. So I don't know if we can, let's just try it. We'll go get media. This thing really irritates me that these buttons move, so I'm just going to do something very stupid and put a line break there. Button stay in place. Connect WebSocket, setup thingy, make a call. That sends our message to the WebSocket. There's no one there to create an answer though. So let's open a new Safari window. A new Chrome. We'll go get media, connect, setup, and make call. And maybe we will receive, so on ad stream on ice candidate, did we? There we go. So we got a setting create answer. So this means that our client received the offer and he started to create the answer. And here's the actual description. So you can see it's of type answer, and there's an SDP, which is the opposite one. That came through the WebSocket. Yeah, the message came on the WebSocket. Makes sense. And then a bunch of on ad stream, on ad ice candidates were called, which we set up initially. And those ones we actually have to handle as well. So it's almost like the STPs were exchanged, and then they suddenly, however, there's no ice candidates yet. All we specified were our ice servers. We didn't, so the browsers are then going to say, okay, cool, well, let's go and fetch those candidates as we discover them. Those also have to be sent between the two clients, so they can begin connecting to each other. Okay, so where we would handle those are on those ice candidates, on ad stream, on remove stream. Yeah. So on ad stream is actually going to get called when the remote end adds a stream to the connection. It could be that our browsers are already, because I'm running this on the same network, we may not need to actually handle the ice candidates, because I can already see that on ad stream is being called. So it almost is like the two sides are offering each other streams. So let's just do something with that stream initially and see what we get. So on ad stream, what we can do is, let's just make another video window, and let's call this one the local video stream. That makes sense. And then we'll create a remote video stream. We're going to give it the name of remote video. So we've got our local one. If we could get media, we get the local. We're expecting the remote one to populate, right? Let's get a handle to this, or do we care? No. So we could probably do a little trick like that. When we get the remote, we get an ad stream. of that side. So what we want to do is get the remote video there and set that to probably the event.stream. Yeah, something like that. Let's see what happens. Just refresh this and that. I'm gonna get, connect, setup, get, connect, setup, and call. I don't know if any remote streams worked here. I'm not 100% sure, it didn't look like it. The one interesting thing I did see in my workings were that not only did we set that source element, but we also went on loaded metadata remote video. So that would be video element, not unloaded, something like that. Let's just try it. Get, connect, setup, get, connect, setup, make call there. No, nothing yet. It could be that our ICE candidates need to be handled. Yeah, so let's do that. Okay. So on ICE candidates, yeah, it is here. On ICE candidate, we get the event, we've seen it. On ICE candidate, it's that guy. We see that this kind of candidate structure. And actually, if you look inside here, you'll see there is kind of address information, maybe port numbers, TCP, that it's going to use TCP. The other ICE candidate might be different. So ICE event, there's another candidate. Look, and this one's got like a different, this has got like an internet type of IP. Whereas that one's got like my LAN sort of IP. So those have to be sent across the wire. This is, I think, why our streams are not setting up. So on ICE candidate, I'm just going to copy some code. Yeah. Okay. Oops. On ICE candidate. So if it is a candidate, I'm going to log it. We're going to then send. Are we in that funny thing? No, so we can go this dot WebSocket.send. Stringify type equals candidate. Candidate event candidate.toJSON. So we're going to send that candidate to the other end. I think there is a legacy reason why there's this end of candidates. I think on ICE candidates can sometimes send you a null there, and that's meant to tell you that it's the end of the candidates. I think that's just really for legacy reasons. So if we receive a candidate, that means now candidates will be flowing over the WebSocket. So let's see where we would handle those. So on our WebSocket, yeah, okay, so here's our offers. Oh, you know what we're not receiving is our answer. So yeah, so this is going to create an answer. We need to handle it here as well. This is potentially a problem. Message.type equals answer. How do we handle an answer? And it's pretty simple. It's the peer connection dot set remote. Remember, we have to complete the loop by setting a remote description of that answer. TC session description message. That's what answer. This actually could be why things weren't working earlier. And then we also have to handle message.type candidate. So if we receive a candidate, what do? We add it to the peers connections, add ICE candidate. And it's a new RTC ICE candidate based on that candidate. Yeah, that makes sense. Okay, so let's see if this gets us any further. We have our two thingies. Let's refresh both of them just for fun. Get media connect and set up. get media connect and set up. This guy will make the call. And did we get anything? A read property, send of undefined on add ICE candidate. Okay, so let's have a look at that. Add ICE candidate. Here's this dot send. Oh yeah, so our this and thatting is getting messed up here. So let's go that WebSocket send there. These all look okay. That one will look okay. Remove and add streams, yeah. Alright, let's clear that. Try that again. Get connect setup. Get connect setup and make a call. Anything interesting? So we've got a whole bunch of candidates. So they execute set remote description. Send. Here's a problem. Okay, so actually the issue turned out to be that in our WebSocket client, WebSocket server was sending messages to a whole bunch of disconnected WebSockets, including the WebSockets, the clients themselves. So what we really need to do here is not have that happen. We probably should just be handling the disconnects of WebSockets better down there and removing them from a list or whatever. But ideally, the client.ready, we should be checking whether the WebSocket itself is open. So I know when we zoom back to where we were having that issue, we were seeing a whole lot of broadcasting. We only had 2 browsers open, yet we were broadcasting more than once, and it turned out we're broadcasting back to the same browser that was currently connected. So just added that line, and we can restart our signaling server. And then if we give this thing a go again, another try, let's see if we can get it to work. So get media, connecting, setup, get media, connecting, setup, and then we can make a call, and there we go. So now you're seeing on the top is the local stream, and you should be able to see a tiny delay. At the moment there is no turn server, so they are literally this client is sending its video stream to this client, which is being displayed at the bottom. That guy is sending his video stream to this client, which is being displayed at the bottom there. So there's a tiny bit of lag in the bottom ones versus the top ones, which is probably just my network, to be honest. So probably it's very low latency for sure. And we are just exchanging this over a turn interface. So that means they are connecting directly to each other. They're not being tunneled through a turn server. Because the 2 browsers are connectable on my local network, they're connecting directly to each other, which is pretty cool. And if we have a look through our dev tools, I suppose we could sort of pull a bit of that picture together. So we should see initially when we open the media, we find the media streams, then we received an offer. So remembering that side created the offer, this side created the offer, and the offer was received on this side. So we received a message called an offer, we created an answer, we showed our answer there, and then we received a candidate which contained a local IP address. Then we received a media stream. We received actually another ICE candidate which probably contained no, we only ever received the local address candidate. And then we had a RPC peer connection ICE event, and this is probably where on ICE candidate. Oh, it's another candidate. And what is that candidate? Answer an offer. Oh, it looks like it was like a 127, even like a local host type of candidate. And then end of candidates, and that was it. And then the streams came together. Yeah. So hopefully you found that stuff quite interesting. It's like good insight into WebRTC and kind of how easy it is to embed media streams into web applications. This also works pretty well on most mobile devices, so it's pretty much a good standard. WebRTC is supported across compatibility. I'm sure we can have a look, find a compatibility, live switch. So it's supported across pretty much most of the browsers. I think IE falls behind, but like the new Microsoft Edge, Chrome, Safari, Android, Chrome OS, it certainly works on iOS even. So on my iPhone, I can launch Chrome and do this. WebRTC. The other cool thing is it doesn't have to only be used for media. It can also be used for just pure data. So I could even transfer data between these two clients. It doesn't have to be media. And that is called a RTC data channel, I think, yeah. An RTC data channel. So this is like if you had a chat interface or something like that, you could also over that peer connection, you could exchange a data channel, which means that you could then just send messages to and from the device. It could, it could be chat. It could be anything. It could be database stuff, like whatever. Anything that you'd like to send between two browser clients. Awesome. Thank you very much for watching, and hope you guys enjoyed that.